Hello and welcome to the lectures on state space approach to control system analysis and design. In this week we are considering the case study of a nuclear reactor, which is in continuation to the lectures in the week before this. And this particular lecture is on fast output sampling based control of the nuclear reactor. We proceed ahead. So this is what we did in the preceding lectures. We considered first a linear output feedback control. Then we considered the periodic output feedback control. Both could be designed and both gave responses to the closed loop system depending upon the relative merits or demerits, which we saw. In this lecture, we are concerned with the design of fast output sampling control for the nuclear reactor, and it will be considered. So at the starting, we should have the system model. So these are the set of linearized differential equations for the nuclear reactor. They are 5 in number, system order is 5. And of course, there is one algebraic equation given by this, which is used to express the rate voltage in terms of this state variable delta V R bar. So we have these equations for the system and the corresponding representation into standard state space form, where A, B and C are the respective system input and output matrices. This is the choice of state. First state variable is change in neutron density from the steady state value, change in delayed neutron precursors concentration from its steady state value, change in linear voltage from its steady state value, change in this state, which is not the rate voltage but a quantity which is a combination of rate voltage. You can see delta V R dot is delta V R and this one. So it is rate voltage and the linear voltage, a combination of that, its deviation from its steady state value and the control rod position, change in control rod position. These are the state variables. The output variables are change in neutron density and change in rate. Of course, at steady state the rate is 0, so change in rate is also the same as rate. Input to the system is the voltage to the control rod, voltage signal to the control rod, which is again 0 at steady state. So delta V and V are identical for the system. Now this system is given. The values of A, B and C are like this. A is a 5 by 5 matrix given like this. B is a 5 by 1 matrix given like this. There is only one input. And C, because there are two outputs, it has 2 rows and 5 columns. So 2 by 5 matrix. This A, B, C is known. And we have already proved in the preceding lectures the controllability and observability of the system. The system is fully controllable and observable. Now with these things in hand, we now are ready to design a fast output sampling based controller. Now before I say that what is the value of the sampling time we consider, I first recall to your knowledge two things. One is this continuous time system, this A matrix has one eigenvalue very large, which is of the order of minus 650. Second thing is that an important consideration in the design of fast output sampling based controller is that we are required to design a state feedback for the system phi t gamma t, which is the discretized system for AB corresponding to the sampling time t. Now that with the state feedback f for the system, this closed loop system phi t plus gamma tf, this closed loop system matrix should be invertible. We require the inverse of this matrix. You can recall, or we will see subsequently. And if it has any eigenvalue at the origin, then of course it will not be invertible. Now coming back to this, the open loop system has eigenvalue at minus 650. And so you can see e power minus 650 into t for any meaningful t will be very close to 0. And what it means that if we design a feedback in order to bring this eigenvalue which is 0 to away from the origin in the z plane, we require a large gain. And the large gain, and that too means it will mean that in the when we look at the corresponding map in the s plane, from minus 650 we want to drive this eigenvalue towards the origin. So let us say minus 400, minus 200, minus 100, etc. But how much difference one expects? E power minus 650t, e power minus 400t, e power minus 100t. To a good precision they mean different, but if the precision is limited, all these quantities are close to 0 only. We have to keep this in mind. So when we are going to design f, at that time we should not face difficulty, and for that reason at the outset itself we should choose a t which is much smaller, so that minus 650 into t will be a number which is at least 1 decade smaller. So for that reason we select t equal to 0.25 second, and of course it is justified from the physical considerations of the system. Because we are sampling the system at this large intervals t, in 250 milliseconds, in 0.25 second, the system output would not have changed much. We can expect that. In fact, we can take it even smaller, that will be better. We should not take it larger. So let us proceed ahead. There is some basis for choice of t. We have chosen t equal to 0.25 second. And for that t, we obtain the system phi t, gamma t. For the continuous time system given here, x not equal to x plus bu, we obtain the discrete time system characterized by the matrices phi t and gamma t. The system is xk plus 1 equal to phi t, xk plus gamma t uk. And of course yk is cxk. So we have phi t given here, we have gamma t given here, and we have c given here. Now the system observability index is 5. Recall that observability index is that nu for which this c phi delta square c phi delta power nu minus 1, and this matrix and the matrix c phi delta etc, c phi delta nu minus 1 and c phi delta nu. It has more rows, you can see. So that largest value of k, let me represent it by some k, for which the rank of this is equal to the rank of this is the observability index, and that k, largest k, is denoted by nu, the observability index of the system. And for this system it is 5, nu is 5. Now for the design of the fast output sampling controller, the consideration is that n should be greater than or equal to nu, and in this case it should be greater than or equal to 5, and we select 5. And correspondingly delta is 0.05. Now we will be required to do the sampling of the output every 50 milliseconds. So that represents a burden. We require a relatively fast data acquisition system. However, here there are only 2 outputs, so it is going to be an easy job to design a data acquisition system to get the samples of output at every 50 millisecond. Anyway, so we select n, we select delta, and we obtain the corresponding system and input matrices for the discrete time system corresponding to the continuous time system model of the nuclear reactor. We obtain. We proceed ahead. Now we have to design a state feedback gain F to stabilize and get good transient response for this system. This phi t and gamma t, they are the system and input matrices for the system sampled at the rate 1 by t, and F is the state feedback gain. So we choose these pole locations. Again, as I told in case of periodic output feedback design, so I told at the time of periodic output feedback design, and even before that when we were talking about pole placement, that this design has to be carried out so that the feedback gains are small. Even though we have chosen this kind of pole locations which are very close to the unit circle, that circumference, still you see two of the gains are very large. But then anyway we proceed with this F, which yields eigenvalues like this. All of them are real, so we then don't expect any overshoot, undershoot in the transient response. Now the next step is to obtain the matrix C0, which is this output matrix post multiplied by the matrix, system matrix corresponding to the sampling at the rate 1 by delta, C into phi delta, then C into phi delta square, and so on up to C into phi delta power n. So because n is 5 and there are 2 outputs, so we get the C matrix 10 by 5. C0 matrix. This is bold C0. We obtain the D matrix next, which is C into gamma delta, then C into gamma delta plus C into phi delta gamma delta, and so on. C into gamma delta and so on. C phi delta n minus 1 gamma delta. This summation. And this boldface D comes like this for the nuclear reactor for the values of phi delta and gamma delta which were there in the one of the previous slides, preceding slides. So we have obtained C0, we have obtained D, we have obtained F, the state feedback gain. Now we are ready to calculate L. So before that we obtain the boldface C, which is this product C0 plus DF and phi t plus gamma t F inverse. This is what I was talking. This closed loop system with the state feedback should not have any pole any eigenvalue at the origin, otherwise this inverse will not be possible. That we have done. We have obtained the f. The smallest eigenvalue is 0.001. It may give some numerical ill conditioning, but the matrix will be invertible. So we have selected f such that this inverse will exist, and so the C, if computed, it comes like this. Now you can see that ill conditioning. Some elements, please see here, of the order of 10 to the power minus 15, as good as 0 here, and some elements as high as 10 to the power 5. So this matrix is having very bad conditioning. The condition number of this matrix is very poor, and likelihood of facing numerical errors. Fortunately, in this case, we are able to obtain a pseudo inverse of the matrix C, and so when we solve LC equal to F, this L, boldface L, is F, and that C inverse, and the inverse we took here is pseudo inverse. And so we obtained this L. Now you see again the effect in L. The elements in L, you can see this is 4 into 10 to the power 4 of that, very large value. This is only slightly smaller than that, negative side, and the smallest values are of the order of 10 to the power 2 or so. So the fast output sampling controller gains are very large, of the order of 10 to the power 4. We should have a design where the gains are smaller. I have been telling this point again and again. For these pole locations, for this design, we have this periodic output feedback gains. One should repeat to obtain good values of periodic output feedback gain, or one can see there are research publications in which there are LMI, linear matrix inequality based approaches for obtaining this L from this equation. And in fact, I forgot to mention while I was taking the lectures for periodic output feedback, that periodic output feedback gain K could also be optimized. There are ways of obtaining optimum solutions for these equations. One can use that to obtain L. However, this is only an example for demonstration. So we are happy by taking a pseudo inverse of this boldface C to obtain L. And so this is the value of L. This is L0, this is L1, this and this L2, these two L3, and this is L4. L0, L1, L2, L3, L4. So L0 will multiply to output at ykt, L1 to ykt plus delta, L2 to ykt plus 2 delta, L3 to ykt plus 3 delta, and L4 to ykt plus 4 delta to implement the fast output sampling gain. And just as a recall, in the fast output sampling, what we do, this is the system. This input, these samples are taken every t by n, and this switch is closed every t second. And over the time, we get the stack of output. So y0 kt, ykt plus delta, and so on. And they are multiplied by L, and that serves as the input Q. So we have obtained this L, and that was obtained for n equal to 5, t equal to 0.25, and corresponding delta equal to 0.05. This L has been calculated. Now we are ready to do system simulation. When we consider the same transient which we have considered in the other cases, for the case of output feedback, simple output feedback design, or for the periodic output feedback design, the same disturbance we consider. The system was at equilibrium at t equal to 0. Then a disturbance voltage is applied at the input terminals, which is of magnitude 0.25 volts or 250 millivolts. It is kept applied for 1 second. Thereafter it is dropped to 0, and for this 5 seconds we are not generating any closed loop control signal. The system is left to behave autonomous. Thereafter we apply the closed loop controller based upon the fast output sampling. And when we do that, this is how the delta V, which is also equal to V because equilibrium value of V is 0, this is how the control voltage varies to the control rod. This is the control rod position. In this portion it was autonomous. When voltage was there, it kept growing with time. When disturbance voltage was removed, the control rod becomes stationary. So its position doesn't change. It is this much. Subsequently, the closed loop controller is brought in the loop. So the correction starts, and the control rod, it will be brought eventually to its equilibrium position in some time. This is how the controller behaves. Now this is the change in neutron density relative to steady state neutron density of 1 unit. The change is very small. Of course, if the controller was not switched on, it would have continued rising exponentially, slow exponential. However, here the controller is brought in the loop at t equal to 5 seconds, and so the corrective action, feedback correction starts. And again, the system will eventually stabilize at the steady state value of 0 as t tends to infinity. In 25 seconds, it is already very close to 0. This deviation is not very large. The corresponding delta V, this is delta V. Same shape, but it is little smooth because of the time constant in the voltage amplifier, linear amplifier. This is the rate. It attained a positive rate because the system was not being controlled. However, it was corrected, and with a negative rate, it is when the system reaches the equilibrium, the rate will also become 0. So it is corrected. So with this, we complete the simulation of fast output sampling based controller. Now we have seen 3 types of controllers: the linear output feedback controller, the periodic output feedback controller, and the fast output sampling based controller. And we see that because that periodic output feedback controller gave a lot of fluctuations in the control input, it is not a very desirable controller. The simple output feedback controller is able to stabilize the system. However, its response is not that fast. The fast output sampling controller gives a good response and corrects the system states without much deviation in their values. So of course, based on this design and simulations, we can always say that fast output sampling controller gave a good response. But we have not considered the state feedback. So one can consider state feedback and its application to the reactor system. As I said, the system model we have taken is a simple model characterized by only 5 states. An actual reactor system, we should consider the control rod dynamics. We should also consider the internal feedback effects. So a good order of the system will be something like this: 5 plus 1 control rod dynamics, 6 plus 2 feedbacks. So 6 plus 2, 8 order system also one should consider. And then this will be designed in the power range operation. Similar design has to be done for the system in the low power range and intermediate power range operation, and a kind of scheme to smoothly switch from the low power regime based controller to an intermediate range controller to a normal power range controller, that has to be built. So this is how the situation in a practical reactor control system design is. This example was only to bring out that we can design controller for nuclear reactor. For a control system engineer, it is like any other system, and any control design is possible once we have the controllability and observability of the system established. Thank you very much. See you again in some other lecture.